focus on is trying to understand how to interpret this generalized chain rule geometrically. So we're going to look at that simple example that we started at the end of class last time and expand on it some more. And then hopefully for about 10 minutes left in class, we'll have time to think about doing some optimization. Let's go ahead and look at that example from class last Wednesday it was, since we skipped Friday. We've got this simple function here, f of xy equals x squared minus y squared. Its gradient is a function of x and y, though I don't always put the x and y there, is the vector whose first component is the partial of f with respect to x. That'll be 2x, and whose second component is the partial of f with respect to y. That'll be negative 2y. So there I have the function that I can enter right there, and its gradient. And I'd like to try to understand this function. In particular, focus on the contour map. I'll make a contour plot of this. There it is. What you see there in the middle is a little bit of numerical error or something right there. That's not accurate. I can fix that by plotting more points. I forget what the default is. It's either 10 or 15 in each direction. So if I make it larger, like 50, for example, that should fix that. Yep. It's a little bit better now. Let's add some more contours in here. 30. There we go. There's a contour plot for this pretty simple function again. X squared minus y squared. Notice it looks like those level curves are all what? What do these look like? Hyperbolas. And that would be the case if you set x squared minus y squared equal to a constant, as long as the constant is non-zero. You can divide both sides by the constant. For example, if x squared minus y squared equals 4, you can divide everything by 4 to get a 1 on the right side to see that it's the hyperbola whose equation in standard form would look like this. When the output is 0, that's where you get the big x through the middle. When x squared minus y squared is 0, y is essentially plus or minus x. And so you get these two lines that make it x in the xy plane. All right, let's add. Let's go ahead and use vector plot to add the gradient vector field to this. So we'll combine those plots with show. Vector plot. Plot a vector field, though it scales the vectors down. Grad f. Again, x going between negative 5 and 5, and the same for y. Oops, let's see. Oh, I think I need curly braces. Since I used curly braces before, I think I need them. Let's see if that fixes it. There we go. So those are the gradient vectors all scaled down by a certain amount. I think it was, scaled. I'm not exactly sure how much it was scaled down. Let's not worry about that. They're all pointing in the right direction, and they all have the right relative lengths. They're pointing from dark to light, pointing in the direction at which the instantaneous rate of change is greatest. It's in the direction of the gradient vector. Those are normal to the level curves at each point, and their length is proportional to the magnitude of the directional derivative in that case. Longer gradient vectors when those level curves are closer together, and shorter when they're further apart. Again, those level curves are drawn based on what's called a constant contour interval. The output of the function increases by a constant rate. For example, in this case, it looks like if I go from this one to the next one, it goes from 11.2 up to 12.8. So that's an increase of 1.6. So it should go up to 14.4 the next one, and then 16 for the next one. Keep going up by 1.6. And when you've got that constant contour interval, when the level curves are closer together, that means the function's increasing more rapidly. All right, but we talked about thinking about this with polar coordinates a little bit last time. Let's do that. Actually, to be consistent with one of the problems in your book that I'm going to talk about here, I'm going to go ahead and call the output U instead of Z. Okay? This is going to be consistent with number 19 in section 14.6 on the chain rule. You might want to look there. It's on page 831. I'm going to be trying to illustrate that fact. In terms of polar coordinates, again, you really should call it a different function if you're going to write this. You probably should give it a different name, but it's related to the original one, so it probably should be related to the name of the original one. And that's why I called it F polar last week. It's representing the same function on the plane. So again, if it's a temperature distribution, for example, it's going to give you the same output at any given point in the plane. But the formula has to be different because you're using polar coordinates to plug in the function instead of rectangular coordinates. But again, the way you find it is you replace x with r cos theta and y with r sine theta. You get r squared cos squared theta minus r squared sine squared theta, which via a double angle formula simplifies to r squared cos 2 theta. Giving you the same outputs, the same U values, the same temperatures, if you like, at every point in the plane, but it's a different formula based on whether you're using rectangular or polar coordinates. Okay, what I'd like to do is I'd like to add more to this picture. Help us understand the relationships between these things. I'd like to make an animation, so I'd like to embed this in a manipulate. That. I need an animation parameter, and we've always used letters to represent quantities that are animation parameters, that are numbers. In this example, I'm going to do something different. I'm going to use something called the locator command that is essentially going to use the cursor as something that can cause the changes, the animation. This is a bit strange, but here's how the code looks. Here's how I'm going to do it. I'm going to put PT in here. That's going to represent the point that the cursor is at. PT stands for point. I'm going to start the cursor at the point 2, 1. It is assumed to be in rectangular coordinates, by the way. And then I'm going to put a comma after what you see there and put locator with a capital L. Locator, and end off the curly brace there. This code is going to create an animation that will, instead of having sliders, use the cursor as what causes the animation. I'm not actually animating anything yet, though. So we just see the cursor. I can move this cursor around, but that's all that's being animated. What I'd like to do, though, is I'd like to put some vectors in here. I'd like to put the gradient vector for one. And I'd like to put a couple other vectors in here. Let's put the gradient in there first, though. So let's see. I can do that with graphics and arrow. Say a thick red arrow. I want it to be based at the location of the cursor, which is specified by PT, point. So that's where the base of the arrow is going to be. Where should the tip of the arrow be? At PT plus the gradient. It's really going to represent the gradient vector. So I'm putting the gradient vector to be based at the location of the cursor. Now let's see, grad F PT. That should do it. Yeah, let's see. That should work, I think. There we go. There's the gradient vector attached. It's fairly long. They'll get shorter when the level curves are further apart, longer when they're closer together. Let's go ahead and scale it down by a certain factor. I'll just scale it down by a factor of 2. I think that'll be good enough. So we'll divide it by 2 to make its length half of what it was before. And again, there's no sliders here. It's a 2-dimensional animation parameter. The cursor is what that does the animation. I'd like to add some other vectors to this picture, and in fact, I'd like to also add a circle, maybe a line segment as well. Let's derive the equation in number 19. I know that was a completion problem, I think, for last Friday. So this is section 14.6. 6, problem 19. Maybe it's one you skipped. Probably shouldn't have skipped it. The algebra is kind of messy. What you want to do is you want to show the squared length of the gradient vector equals, and here they use the subscript notation for partial derivatives, the partial of u with respect to r squared plus 1 over r squared times the partial of u with respect to theta squared. I'm going to go ahead and use this Leibniz notation here because I think it's a little less confusing even though it's more writing. The partial of u with respect to r looks like that, or you can call that du dr if you like. That's being squared. Add on 1 over r squared, where r is the polar coordinate, the radius, the distance to the origin, times du d theta squared. The claim is that this is true, where this would ultimately be du dx squared plus du dy squared. How do you do such a thing? Well, you need the chain rule. You need to figure out how you can simplify this in terms of x and y. U depends on x and y. And x and y both depend on r and theta. I think it's a good idea to draw a diagram like this to help you get the higher dimensional chain rule right. And by the way, the diagram generalizes. You could have 5 variables in the middle and 3 variables in the bottom. And you'd have to draw all the line segments, all the possible dependencies. It would be a mess. But technically speaking, to get that higher dimensional generalized chain rule right, you want to draw that diagram. Helpful. Put the partials that correspond to the derivative of the top variable with respect to the bottom variable along each line segment. And again, the purpose of this diagram is to help you get the formula right. Be careful that you label right. You see that okay? If I want to find partial of u with respect to x, excuse me, with respect to r based on this diagram, I need to look at all the paths through the diagram that go from u down to r. And there's 2 of them in this case, this one and this one. Though if you had 5 variables in the middle and 3 variables on the bottom, there'd be more than 2 paths through the diagram to get where you want. Multiply the partial derivatives along each path through the diagram from the top variable to the one that's at the bottom there, and then add the results. So it's du dx times dx dr, multiplying along that path, plus du dy times dy dr, multiplying the partial derivatives along this path. By the way, this is a situation where the intuitive approach to differentials is not a good thing. It can lead you astray. Remember, the one variable chain rule can be written like this in Leibniz notation. dy dx is dy du times du dx. And again, the intuitive approach to differentials is to treat those as individual quantities and fractions and pretend like you're canceling the du's. That doesn't quite work here. I mean, you cancel these dx's and these dy's to get du dr plus du dr equals du dr. In other words, does du dr equal 2 du dr? No, it doesn't. So again, this is a warning. This is right, but if you think of it intuitively, it can get you into trouble. You don't need a factor of 1/2, for example, in front of these things. Again, we're thinking about this in the context of polar coordinates. So the dependence of x and y on r and theta is definite. We've got definite formulas here. Let's erase the one variable version up there. X equals r cos theta, y equals r sine theta. Showed you this last week. Dx dr, treat the theta as a constant, is just cosine of theta. And dy dr, treat the theta is a constant here, and you get just sine theta. So this becomes cos theta du dx, cos theta is that, plus sine theta du dy, sine theta is this one. Either way, you can think of it as a dot product. You can think of this as cos theta, comma sine theta, dotted with du dx, comma du dy, which is the gradient vector. And that's going to help us give some geometric meaning to this. Let's do the other one too. I'll come back over here. I don't think I want to completely erase that. Way over here, what's du d theta? Again, go through the diagram. Go from u down to theta. There are once again two paths through the diagram from u to theta, either via x or y. And so the appropriate partial derivatives are these. Okay, look once again at the conversion equations from polar to rectangular. dx d theta, differentiate r cos theta with respect to theta, treat the r like a constant. That's going to give you negative r sine theta, and then multiply that by du dx. Differentiate y with respect to theta. Y is r sine theta. Treat the r as a constant. You're going to get r cos theta. And this can also be thought of as a dot product. And you can also factor the r out in front. R times the vector negative sine theta cos theta is dotted with the vector du dx du dy, which is once again the gradient vector. These other vectors that you see here with the sine theta and the cosine theta are, excuse me, special too. For one thing, if you know the r there, they're unit vectors. This thing's a unit vector, right? Way back over here, this thing's a unit vector too. And in fact, they are also orthogonal to each other, no matter what theta is. The dot product of this vector with that other vector over there, negative sine theta cos theta, is always going to be 0. Kind of like that two-dimensional trick with unit normal vectors. Switch them around and put a negative sign in front of one of them. In this case, you put the negative sign in front of the first one when you go from here to the one over there. They have special symbols too. This one's often called E sub r. And the one way over here is often called E sub theta. They both depend on theta, functions of theta, but that one's called E sub r, this one's called E sub theta. This is not the number E. This is not eccentricity. Why the E? Well, sometimes in math, E is a letter commonly used for unit vectors. These are unit vectors. And that's the origin of this notation. Let's put these vectors in the picture too. With this one, I'll multiply it by r as well. So we'll continue with the graphics and the arrow to include those. And in fact, I think I'm even going to define those to be functions. Let's see, let's use the palette here to define two functions. I'll use a subscript just like I do by hand. E sub r of theta is going to be the vector whose first component is cos theta and whose second component is sine theta. And then the other one, E sub theta. These subscripts are not going to be variables, they're just labels here. I didn't have to make subscripts, and maybe that would have been less confusing than what I usually do. But I've started to type it now, and so I guess I'll keep it that way. This one's negative sine theta, comma cos theta. Let's get these in the picture. So we'll continue this type of stuff here. Be careful not to make a mistake. Let's see, the square bracket goes with the arrow. So I'm going to copy and paste this stuff right here, starting with thick. Put a comma over here, paste it. Use a different color like blue. Use a different vector. Let's use here, let's make E sub r of theta be the vector. But if you think about it, putting a theta in there is not going to be helpful, at least based on how I've constructed this. Because what is theta? I want theta to change as the point moves around. How do you find the angle from the point? You use the arctangent function. Arctangent of y over x will work if what? What's necessary for arctangent of y divided by x to work to give you the angle? Gotta be, yeah, gotta be in the first or fourth quadrant. That's the range of the arctangent function. So you might think we have to deal with this in a piecewise way. However, there's actually a trick in Mathematica. You can still use the arctangent function. I think I showed you this trick before. If instead of y divided by x, you put x comma y, that will work and give you an angle in the second or third quadrant if your point is over it. I think the default outputs for the arctangent of blank, comma blank, x comma y is between negative pi and positive pi. I don't think it goes 0 to 2 pi. So I'm going to put an x comma y in here, but what are x and y? Well, they're the first and second coordinates of PT, the point. Here's how you type that in. PT of 1 with double square brackets, like this. That represents the first entry in PT, the point. Technically speaking, that's a list in Mathematica. This is the first entry in the list, but I can think of that as the x coordinate of the point. Comma PT of 2, that is the second coordinate of the point. So this is going to work at least as long as the point is not at the origin. I'm not telling you the truth, I'm not sure what happens at the point of the origin. I guess I can test that. Arctan of 0, 0 probably is undefined. Yeah. What's the angle of the origin? Okay, it's undefined. But I don't think we have to worry about that here. Here we go. There is E sub r. This vector here, cos theta, comma sine theta, right there, its unit length, which on this scale does seem about right. So its length doesn't change as I move around, but its direction will. How would you describe its direction? The blue vector. Points are directly away from the origin, yeah. In fact, I think I am going to take the time to go ahead and put something else inside here with graphics. Maybe I'll put it at the start so it's less confusing. Thick, black line. I'm not going to make an arrow, I'm going to make a line segment going from the origin to the point to see that that blue arrow is parallel to that black line no matter what. I have another reason for putting that black line in there. Okay, so the blue vector points directly away from the origin, has the same length of 1 no matter where I am. Let's also put another arrow in there in the direction of E theta. Well, let's go ahead and also multiply it by r so that the vector gets longer as I go further away from the origin and shorter when I'm close to the origin. Still need to explain, by the way, how to derive this, what it means. Still need to do that. Haven't done that yet. Let's see again, be careful not to make a mistake. This one ends the ER, this one ends the arrow. So I'm going to copy and paste starting just to the right of this one. Let's make it green. Let's put an E theta here. How am I going to get the R in there? I can't just do that, right? Because what is R? Mathematica doesn't know. How do you think I deal with that R there? Yeah, use the fact that r is the square root of x squared plus y squared, which in this case is pt1 squared plus pt2 squared. So we'll replace this r with the square root of pt1 squared plus pt of 2 squared. So there's that green vector there. That's not a unit vector, unless I happen to be on the unit circle, which would be right about here somewhere. Probably right about there. The green and blue vectors are the same length. The length of the green vector is the same as the length of the black line. It's the value of r. Let me add one more thing to this picture. Let's add a circle of radius r going through the origin. Let's see. Pick maybe magenta circle. Centered at the origin with a radius of r. Go. All right, now we got to come back to number 19. Talk about deriving this, and then we'll talk about the geometric meaning of all this. I'm not going to derive it fully, but just give you an indication of what to do. Maybe I'll put it behind the screen here. The algebra is pretty messy, but it's not the worst kind of algebra you've ever done. Because of the chain rule, du dr squared plus 1 over r squared du d theta squared, by the equations we already derived here. Here's du dr right there. So if we square that, we get cos squared theta du dx squared. These are not second derivatives here. These are squares of first derivatives. Plus 2 cos theta sine theta du dx du dy. I'll go into the next line since I'm out of room here. Plus sine squared theta du dy squared. That is the square of this thing right here, using the FOIL method. When I use this 1 over r squared times du d theta squared, the r's cancel. We square this back over here, you get a factor of r squared. That'll cancel with the 1 over r squared. And you can effectively square this without the r's. Notice the minus sign, though, that's important. You end up getting plus sine squared theta du dx squared minus 2 cos theta sine theta du dx du dy plus cos squared theta du dy squared. And I hope you can see where this is going. That cancels with this. And then you combine these two things together to get a du dx squared, factoring out the du dx squared first, and then using the fact that cos squared theta plus sine squared theta is 1. Do the same kind of thing with these two terms. They go together. And we have now algebraically confirmed number 19. This equals that. But now what's the geometric meaning of it? Okay, this algebra is all fine and good, it's important. But how can we understand all this with this picture? We'll think about both this equation from number 19 and these equations that you see right here for du dr and the other one for du dx. Let's think about this one first. Intuitively, what's going on? Why do we have to divide by r squared is one question. Right there, but not there. Why do we have to do it at all? Essentially, the intuitive reason is when r is very large, when you're far away from the origin, a small change in the angle can produce a big change in the position of the point, which could therefore produce a big change in the output of the function. So, this division by r squared is kind of a compensating factor for that. The further you are away, if you did not have the 1 over r squared there, u theta would tend to be very large, even for small changes in theta. Well, okay, when I think about changing the function, that could have a big effect on the output of the function for even small changes in theta. That's what I wanted to say. When you're far away, because again, a small angle change could produce a large motion in the plane. Whereas a change in r doesn't have that kind of effect. A change in r is a change in the distance from the origin. It doesn't matter what theta is. The change in the r doesn't, for a given theta, the change in r doesn't affect the distance that you travel. Okay, so it's going to have the same distance no matter what, whereas again, a change in theta is going to have a bigger change in the position of the point when r is large. So you have to divide by this r squared. That's the intuitive reason. It's certainly not a proof, but it's intuition behind why you would need to do that. What about the other equations here, like this one, for example? Well, if you think about dot products geometrically, there's the fact that d dot w is the length of b times the length of w times the cosine of the angle between them. Let's call it something different from theta, like alpha. That can be applied here too. And the length of that vector is just 1. So this is really the same thing as the gradient, the magnitude of the gradient of u, times the cosine of the angle between the gradient and ER, which is not going to be the same as theta. Let's call it alpha. Coming back over here for this one, du d theta equals this, and that is also can be written in terms of magnitudes. Again, E theta has a length of 1. The r's got to stay there. R times the magnitude of the gradient times the cosine of the angle between E theta and the gradient. E theta is 90 degrees rotated counterclockwise from ER, and that works no matter where you are, so I can replace the alpha with alpha plus pi over 2. Which, by the way, is the same as the negative of the sine of alpha. Let's see if this makes sense by moving the point around. So you're thinking about how is u changing for small changes in r and theta. And if r changes, that means you're just moving a little bit further away from the origin. The black line is getting a little longer. Let's move over to this point. Actually, let's re-enter this code to be at the starting point 2, 1. So this point has rectangular coordinates 2, 1. Its polar coordinates, the radius would be square root of 4 plus 1 is square root of 5. And the angle would be the arctangent of 1/2. That's not a special angle. That would be in the ballpark. It looks like it might be 30 degrees or so, but it's not exactly 30 degrees. If I move a little further from the origin, if the black line increases, did the function increase or decrease? As I went a little further away from the origin there. It increased. du dr is positive. Is it increasing faster for small changes in r near this point, or faster for small changes in r near the second point? The second point. Okay, we are thinking about du dr, so we're thinking about this equation right there. In other words, the gradient vector, its magnitude, and the angle that these two things make with each other have the effect on this rate of change, dUdr. When I get further away from the origin, the gradient vector, which is the red vector, does get a little longer because I'm on level curves that are higher values of the function where they're closer together. So the gradient vector gets a little longer, and also the angle changes a little bit. Does it get smaller or larger? I think it looks like the gradient vector is going to point as I go up this way. Can't really tell very easily. Which direction is the gradient vector going to move? It's going to rotate clockwise or counterclockwise? Move away. It's not changing much. It looks like maybe it's rotating a little counterclockwise. It looks like the angle's getting a little smaller. Which is consistent with this because as the angle gets smaller, the cosine value gets closer to 1. So as I move further away from the origin, both of these quantities get bigger. And my rate of change in the r direction therefore gets bigger. How about now for small changes in theta? Go back to my original, re-enter it here. If I change theta a little bit, stay on the same circle centered at the origin, but move around the circle a little counterclockwise, is u decreasing or increasing here? It's decreasing because I'm heading toward darker. Does that make sense with this equation way over here? R is positive, this length is positive, but this quantity is negative. The angle between E theta and the gradient is the angle between the green arrow and the red arrow. It's bigger than 90 degrees. Cosine of that angle is negative. Also, you can think of it this way. It's negative sine of that angle, which is a negative number. So the rate of change is negative. If I made r a little bit bigger before changing theta, what's going to happen? Well, if I go in the same direction outward from the origin, the gradient vector does get a little longer. So r is increasing and the length of the gradient vector is increasing. The angle between the red and green vectors, it's hard to tell. I guess that probably is decreasing a bit. It's hard to tell. The red vector is not changing direction too much, at least. These two things increase in value. This is hard to tell. If the angle is heading toward pi over 2, which I'm not sure if it is or not ultimately, this would be approaching -1 in value. It's certainly still negative, and it's becoming more and more negative as if I move further away from the origin before changing theta. So this r does have an effect. If I move further away from the origin, small changes in theta, again, are going to correspond to larger motions around the circle, the given circle center. That's a lot to try to take in a small amount of time. If you're really going to understand this well, you're going to want to spend time thinking about it. We all have lots of time, right? Well, at least the project will be done by tonight, and theoretically that could give you at least a little extra time, maybe even 20 minutes, just to spend experimenting with this and maybe trying other examples too. All right, for the last 10 minutes of class today, let's go back to optimization. We talked about this almost 2 weeks ago. We were talking about density functions. Two main goals when we had density functions, imagining a sheet of metal, effectively two-dimensional. We had two main goals with that, trying to optimize the density function, figure out where the sheet of metal is most dense, ignoring practical realities of how to make such sheets of metal. Don't worry about it. You want to optimize it. Where is it most dense and where is it least dense? And when we get to the next chapter, we'll want to talk about how to integrate such a density function to find the total mass. And again, I put the word mass in quotes because this doesn't have to be a sheet of metal if you're trying to find the mass in kilograms or grams. It could be a city that's in the shape of a square, and the density function is a population density. people per square mile, per square kilometer. And the mass then would be a total number of people rather than an actual mass. So that's why I put the mass in quotes. Here was the function. Here are its partial derivatives. And we did various things. We made plots, three-dimensional plot, a contour map. We made lots of other things here that you can open up and look at if you like. I'm closing these so that we can see them better. And way down here, before class today, I made a new section on optimization. Just remind ourselves what these partial derivatives equal. And actually, yes, about 2 weeks ago or so, we did actually set these equal to 0 and tried to solve for x and y, though we didn't finish the problem. And I'm not going to finish it completely by hand today either. However, let me remind you of the idea of what I did. Setting -10 plus 3x squared plus y squared equals 0 and 3 plus 2xy equals 0 results in a system of two equations and two unknowns, which typically is going to have finitely many solutions if it has any solutions at all. It's nonlinear, but we can take the second equation, for example, and solve for y in terms of x. Y will be -3 over 2x. And then we can take that and substitute it into the first equation in place of the y to get -10 plus 3x squared plus 9 over 4x squared equals 0. This is valid as long as x is not 0, which we assume for the time being. And then, if you multiply everything there by x squared, you get a fourth degree equation. 3x to the fourth plus or minus 10x squared plus 9/4 equals 0. And also multiply everything by 4 to get 12x to the fourth minus 40x squared plus 9 equals 0. And because there's no cubic or linear term, this can be thought of as a quadratic in the quantity x squared. X to the fourth can be thought of as x squared squared. You can use the quadratic formula to solve for x squared first, and then take the plus or minus square root to solve for x. You'll get x squared from the quadratic formula is 40 plus or minus 40 squared is 1600 minus 4 times 12 times 9. 12 times 9 is 108, times 4 is 432. Over 2 times 12 is over 24. This becomes 5/3 plus or minus square root of 1168 over 24. Last class, I think 1168 was like 16 times 73. Square root of 1168. Now you get 4 times the square root of 73. So this can be simplified to 5/3 plus or minus 1/6 times the square root of 73. I can put that at the top as well. Both of those are positive numbers. You can take the plus or minus square root of both of those to get all possible x's, which are going to be 4 of them. This is representing 4 numbers here. And then you find the corresponding y's for those 4 real numbers using this equation. It's a bit of a mess, but not too terrible. Let's confirm it was solved, and m-solve to get the numerical approximations. Solve is actually going to produce some pretty complicated looking things here. Solve the system of equations. Fx equals 0, I need double equal signs. Fy equals 0, solve that for x and y. Ends up being pretty complicated looking, but I do see some promising things in here. For example, I see a square root of 73 over 6. I see a 10/6, which is the same as 5/3. The y's become more complicated. I'm pretty confident this is giving us the same answers. NSOLVE will approximate those. There we go. Those are 4 critical points for the contour map of this function. Let's see, where's the contour map? I guess up here. One of the critical points is right there. That's going to be a local max. If you imagine a 3-dimensional plot, there's going to be a hill right there with a peak. About there. Remember the graph, the 3-dimensional graph is going to be in front of the screen here and sideways. This is going to be a local min, a valley. A bowl-shaped valley at least. We've got 2 more critical points, one right around here and another one right around there. Those are going to be saddle points. They're called saddle points. And it is as if, okay, I want to get on a saddle, like if there's a saddle point there, how should I sit on the saddle? Well, I have to imagine myself sideways. I gotta sit so that one leg, my right leg is going over there and my left leg is going down there. Then I'll be sitting in the saddle, because the function is going to decrease in my leg's directions. And increase this way, I'm sitting facing that direction, holding the front of my saddle like that, okay? There would be a saddle point about there. It's one of the critical points. There's a second derivative test that's going to confirm that's a local max, this is a local min, and these 2 points are saddle points. What about the global max and global min? It seems apparent, actually, if you think about it, that those are not going to occur at these interior local critical points. Local max, local min, or saddle points. If you look at the shading, it seems that the local min is going to occur in the upper left and lower right, upper left and lower left corners. And the global max is probably going to occur in the upper right and lower right corners. Okay? The domain here is a square, which is called a compact set. It's closed, meaning it contains its boundary. And it's also bounded, it doesn't go off to infinity in any direction. There's a theorem called the extreme value theorem that guarantees that global max and global min will occur. And will either occur at interior critical points or along the boundary somewhere. For this one, it will occur along the boundary. Global max, global min. Okay? So that's the main subject for class on Wednesday. We're also going to consider higher dimensional examples and consider domains that are cylinders instead of squares or boxes.